All right. Yeah, morning, Lily, but we've already started talking about this problem. This is 2017, number 2.
Yeah.
2 ways you could set up the experiment. Now, for part A1, which is draw the diagram and identify what you're going to measure. If you're doing it this way, you would say, I'm going to measure the force using a spring scale. You name the whatever equipment you're using, some kind of force sensor, but a spring scale would work. So you mention that and say what you're measuring. I'm measuring the force it takes just to get the block to start moving. And I can do that with a spring scale. Do you need anything else if you're doing it this way? Do you need to measure? Do you need to measure anything else? If we can get the force of the spring scale and we get some number of newtons. Now you may be saying you're going to set up a graph, and so you're going to do multiple trials and get different points. You might even put different weights on it to get different normal forces. There are a whole lot of things you could say, but this is the basic idea. If you get the force of the spring scale, we're saying that's equal to the force of friction. So now you have the force of friction. What about the normal force? Do we need to measure that?
Yeah.
How do we measure that?
Well, you find
The normal force is equal to mg, isn't it? So if you get the mass of the block on a balance scale, that may be the other thing you'd want to measure. Is the weight, or measure the mass. Measure the mass in kilograms, and then times 9.8 would give you the mg. So those 2 things you would measure, and you use a balance scale. Name the equipment. Don't just assume that everybody knows how you get mass. I'm going to measure that with a balance scale. I say that because on your test, some of you just wrote things like scale. I'm going to measure the mass with a scale. Everything you measure with is a scale. Scale is a general term that means I'm going to measure something. What kind of scale? A balance scale if you're measuring mass. Put the right words in there. Okay, spring scale, balance scale. All right, don't just say scale. That could be anything. If you're doing it this way, now you're saying that what you're going to say is that the mgx is equal to friction, right? And the mgx is mg times the sine of theta, and that's equal to friction, which is mu times the normal force. And the normal force is equal to mgy. I'm doing all this for a reason, and mgy is mg cosine theta. Okay, so this is what, if you're doing the inclined plane method, this is what you're going to do. And look, you don't have to measure the mass because the m's cancel out. So if you're really going to do it this way, it's probably better if you don't say we're going to measure the mass. Now, if you did say that, the person grading your problem would just kind of chuckle and say, hey, this student must have not realized the m's cancel out. Because you can put the m in there if you measured it and it's still right. But certainly you don't need to. The only thing here you'd have to measure is the angle. You've got to measure theta somehow. You already know what g is. Yeah, so all you need to do is measure the angle. If you work the math down here, you end up with the mu is equal to the tangent of theta. Is that true? I think that's true. Because sine over cosine. Sine divided by cosine is tangent. And the g's would also cancel. There you go. So yeah, that's it. So if you're doing it this way, you've got to come up with a big protractor, or of course you could measure the length of the board and the height and use trig to get the angle. But you need to, and if you're going to do that, then you're going to say, I'm using a meter stick to measure the length of the board and the height. That's the length, that's the height. And then I will say the sine of theta is the opposite height over the hypotenuse L. So you measure those 2 things. Or if you're just going to say, I'm going to get a great big protractor and set it up there and read it, then you would say, I don't need a meter stick. I'm going to use a protractor to get theta.
How big is a protractor?
But you have to come up with some way to measure theta. What?
How big of a protractor would you need?
I don't know. If this is a great big board, if you got a little protractor, it might look like that. And that can still do it, but you lose some accuracy with a little protractor when you've got a great big board.
Guess you better get a big protractor.
How big do they make those?
That should be in your standard lab.
I've seen big protractors.
Like that big?
I might be exaggerating.
No way.
Okay. But in A1, you've got to come up, if you did it this way, come up with a way to measure theta and what instrument you would use. If you did it this way, talk about using the spring scale to get F and the balance scale to get M. That's A1. A2 then is the procedure, and we've already talked about that, but depending again on which way you're doing it, you would describe what you would do. If you're doing it this way, you need to say, I'm going to pull it until it just begins to move and read the spring scale at that instant. If you do it this way, you would need to say, I'm going to try it at a small angle, it doesn't move, and then increase it at really small increments until I get to an angle that it does move. Okay, so that should be in the procedure. Number 2, A2. Any questions about A? B says derive an equation for the coefficient of static friction in terms of quantities measured in the procedure from part A. So again, that depends on which way you're doing it. If you're doing it this way, this would be it. That would be the answer to B. If you're doing it the inclined plane way. If you're doing it that way, then you would say the friction is equal to the force of the spring scale. And see, that could be in your answer because that's something you measured. What it said again is in terms of quantities measured in part A. So over here, that was a thing I measured in part A, theta. Over here, the force of the spring scale is something I measured. So that can be in your answer. So again, this is mu times the normal force is equal to the spring scale. And so mu would be equal to the force of the spring scale divided by mg, because the normal force is equal to mg. So that, I think, would be your equation if you're doing it on a horizontal board with a spring scale. Okay, what was the question about part B? You're just solving it for mu. Okay. Now, there's a data table after part B. The physics class consisting of 6 lab groups wants to test the hypothesis that the coefficient of static friction is equal to the coefficient of kinetic friction. When you read that, what do you think?
No. Craziness.
Of course it's not. You already know, but they're not asking you if they're equal.
They're saying
We've talked about this. Make sure you answer the question. They are not asking you here, are they equal? So I keep reading. Each group determines the coefficient of kinetic and static friction between the board and the block, and the group results are shown below. So you look at the data table, there are 6 groups, that each one comes up with a mu s and a mu k. So you're looking down that list, and at the bottom is the average. And you see, oh my goodness, the averages are equal. Did you see that?
Yeah.
Did that throw you off?
Yes.
No.
Did that cause a bit of pause?
No.
Wait, they shouldn't be equal, you say? Now,
I said they're not.
question C. Based on these data, what conclusions should the students make about the hypothesis that they're equal? Now, if you just look at the averages, you're going to say, ooh, based on our data, they are equal. Did anybody check that one?
No.
No, I hope you didn't. You should check the one that says they're not equal, but you have to explain why. What's the deal, Claire?
Group 5 has messed up the averages.
Team 5 was probably, no, I'm not going to point. Team 5 messed up. You're right. If you look at the numbers, every group has a smaller number for kinetic, except for Team 5, Group 5, right? So they all got a smaller number for kinetic. But group 5 is so messed up that they made the averages come out to equal. Yeah. So you needed to explain that. What would you do if this was really our class and we put the data up on the board? What would you
We
do?
have a big long argument.
We would leave it out of our calculation.
You would omit the data from group 5. You'd say, well, obviously that is way different from everybody else's, and so we're going to assume that was big error, and you would just omit that. And if you omit that, the averages would come out looking reasonable. Okay. So that's what you should have written for the justifying the reason. I wrote group 5's data should be thrown out because it is so different. Groups 1 through 4 and 6 show precision, which means similar results. Based on their numbers, the static coefficient is greater than the kinetic coefficient. All right, that's C. Then we get to D. A metal disc is glued to the top of the wood block. The mass of the block disc system is twice the mass of the original block. Does the coefficient of static friction between the bottom of the block and the board increase, decrease, or remain the same? What did you put for that, Nate? How many put remain the same? You're all correct. Did you put remain the same, Steve? Steve, are you dozing off to sleep during physics class? You can't do that. Don't do that. Even though I know Sarah was dozing off over there a second ago too. You weren't? Okay. I just made that up to try to make Steve feel better.
Oh.
Um,
You called me out.
No, I'm just kidding. I didn't call you out. Well, I kind of did, but I was just joking. Remain the same. Kyle, how do you explain that it would remain the same? There's more mass.
It's the coefficient of friction is only changed by the surfaces.
Well, that's true. What you have learned is that that's what this depends on. How rough or smooth the surfaces are. So it's okay to say that. Also, mathematically, what happens to the masses? They can't say like over here. They all cancel out anyway. If the mass was greater, it doesn't matter. It's going to go away. Okay. But you probably should, somewhere in your explanation, again, I don't have the rubrics, I'm just telling you what I think, but I think you should have mentioned for sure that the coefficient depends on the roughness or smoothness of the surfaces, not the mass. Okay. What I wrote was more mass increases the normal force, but also increases the force of gravity on the block, which is true. See, these are still equal. If there's more mass, that's going to be more, but it also increases here the force of gravity. I just said that. The increase in forces cancel each other out when calculating mu. As stated in part B, theta is the only variable that determines mu on the inclined plane. So that's the way I did it. Okay. I want to finish reading that. Any questions about that problem?
Okay, how can theta be the only variable that changes mu if, like, the surfaces stay the same? Shouldn't mu be the same no matter how tall or steep? Sorry, whatever.
It will come out different if you put a different block that's like smoother or whatever, then it would come out different. Yeah.
But if you have a different angle, shouldn't it be the same? You get the same block and the same board.
How do I answer that question? I don't know. I don't have an answer to that right offhand. I'll have to think about it. Sometime during chemistry class, I'll think of a good answer. Because in chemistry, I don't have to think.
Oh.
Is that true? No. It's because in chemistry, and I'm not going to talk about that.
Wait, no, you gotta tell us.
Do a lot.
They're doing a lab,
Is that
and I'm not teaching them today. They're doing a lab where they're sitting there doing stuff, so I can think.
They're doing the lab we did in the lobby last year.
They're doing the cut and glue. Did you do it in the lobby?
Oh.
Because of the clear. You should let them do it in the
Okay,
just for-
let's go to the practice exam. Pull that back out. We were not finished with number 3 yesterday when we were going over the practice exam. Let's go back to number 3. Number 3 was probably the second worst.
Oh.
Number 2 was the worst we did.
Yeah, number 2 sucks.
Number 3 was probably the second worst.
I did really good on the first and last one, but the middle one
This
is
is the first
great.
I actually did the best on number 3.
The very last one was the one we did the best on.
Which was
Did
the
you all
worst?
think the last one was the easiest?
Yeah, it was super easy.
It was the easiest.
I'm sorry. Oh,
The
wait.
last one was good.
Second to last one, no. And number 3 I did best on, so.
All right, number 3.
Congrats.
You did best on number 3? Way to go. Well, number 3 was broke the
Way
other part.
bad.
All right, we already talked about A and B yesterday, so we're going to part C. Remember, this is this container of some kind of oil, and there's a steel sphere that is allowed to fall to the bottom, and then you got this graph where this is energy lost, and this is stiffness, and you got these points that kind of did that, and there was up here an E max. Okay. And we've already talked about it. We're not going to go back and do those again. So let's look at C. One of the scientists, in trying to represent the relationship between oil stiffness and mechanical energy lost, writes down the equation E lost equals CS squared, where C is a constant. And another scientist points out that this equation cannot be correct. Give 2 reasons why that equation cannot be correct. Now, my battery's getting low, Lily, so if it goes away at some point, sorry.
I said we could use my Surface.
Or a charger.
We could
Just
plug
plug
it
it
in.
in.
You think it'd reach there?
It-
Yes.
I don't know.
Okay. All right. Somebody give me one reason why CS squared cannot equal E lost. What, Sophia?
Because, like, E lost has a maximum, and if CS squared equals E lost, then E lost would just, like, become greater into infinity, but it has a maximum.
Yeah, exactly. That is one reason. The fact that it maxes out here, it never will get higher than that. But according to that equation, it has no maximum. That is one good response. Another one, I'm plugging this in, Lily, if you wonder why it's moving around. Another good response might be what? What's another one, Sarah?
The curve is not exponential on the
Yes.
graph, so, and that equation suggests it is.
Yes, that you could talk about the shape of the graph itself, as that doesn't fit this. Exponential, would look more like that, wouldn't it? If it really was proportional to S squared, and this was S, then it would look like that. If you plotted E versus S squared, that would be a straight line, but it wouldn't be this. Okay, so yeah, you could talk about the shape of the graph. Let's see what the rubric exactly said. It said, this is part C on number 3. Wow, I'm on the wrong page. You could have said the equation indicates E loss increases indefinitely. That's what Sophia said, but the graph doesn't do that. Or you could have said the equation represents a parabola, which does not match the graph. That's kind of what Sarah said. Or you could have said it doesn't make physical sense that E loss could be more than the available energy, which was MGD. In other words, you can't go past this max. Any of those things would have been good. 2 of those would have been good answers. All right, go to D. Further attempting to model the ball's motion, the scientists write the following equation. This time it's time equals Z over S. S for stiffness. Z is a constant. Is this equation plausible? Does it make physical sense? Now, of course, you should have said what? Is it plausible? No. Why not? Somebody tell me why you can look at that and tell it's not plausible. Why? I called on you last time, I'm calling on Tony this time.
Oh, I think I got it really wrong for explanation. But T is they're like what's called
T and S are
T and S are
proportional
not
now.
proportional.
Inversely
In-
proportional.
inverse
In this equation they are. So, Tony, are they really inversely proportional?
They are proportional
If you increase
Because
stiffness,
and time. Yeah.
that would slow it down, wouldn't it?
Yeah.
So that would increase time. Does that make sense? If you increase stiffness, in reality, if you make the oil stiffer because you got colder, that's going to increase the time it takes to fall down and go slower. So this is not true. This looks like if you increase stiffness, it would take less time because this equation looks like it's inverse. Everybody get that? That's what you needed to say on part D. You got 1 point for a statement that the equation indicates that T increases as S decreases, or you could have said they're inversely proportional. That's 1 point. Second point for a statement implying that time should be larger as S increases, but it goes on to say, if you simply said not plausible, and then you mention either of those statements, you got all the points, which is 2. Okay, E. Change in kinetic energy, delta K, is the change of the ball between the time it is released from rest and the time just before the ball strikes the bottom of the container. So here it has 0 kinetic energy, but it has some as it's about to hit the container. That's delta K. How much did it increase? On the axes below, sketch delta K as a function of S for oil stiffness, and I think you all see that you should have made a graph that looked, if this is delta K and this down here was time, it should have done something like that. What you know is, as time goes on, no. Is this time, or is this time really, or is it stiffness?
Stiffness.
It's stiffness. I wrote the wrong thing, sorry. Not time. Okay. This is S. There you go. Now it makes sense. If you increase stiffness, the stiffer the oil is, the slower it's going to go, so the less kinetic energy. But up here where stiffness is small, it's going to still have a great change in kinetic. It's going to get faster because the oil is thin, less stiffness. It's going to go from 0 to a big number. But way up here where it's really stiff, then you drop it in and it goes from 0 to a small number. It never does get very fast. So you should know it's going from high down to low. Now, here's what the rubric says about grading it though. You got 1 point for drawing concave upward curve, not a straight line. That's kind of, if something is inversely proportional again, that's what it looks like on the graph. Two things that are inversely proportional don't do that on a graph. They do this. Okay, so that's the only reason, maybe, or maybe you know more from calculus, but just knowing it's an inverse proportion should make you curve it that way. Then the second point was for having the maximum value of K at the lowest graphed value of S. In other words, this should correspond kind of with this stiffness, wherever it was. That's where that should be. And the third point was for not crossing the x-axis. It couldn't go below. And I don't think anybody missed that, but if you made your line go below the x-axis, you lost a point. Okay, out of time. Time to go. See you later, Lily.